Okay, folks, it's time for our next online lecture. Today, the big topic is electromagnetic waves. So, this is the start of a big and important topic, the last big important topic for this class. Um, so, um, let's just remind ourselves a little bit what we were talking about last time. And last time, we just to get up to speed, last time we were talking about the pointing vector, and we talked about how the pointing vector can be written as E cross B, and it gives us power. It tells us the flow of energy. So it's basically power per area. Sometimes we think of it as an intensity, but it's power per area. It's a flux of energy. And we also talked about momentum. We talked about how we can have a momentum density, which was written like this. You can think of it as being proportional to the pointing vector, but it's not a flux, it's a momentum density of an electromagnetic field. Momentum density of an electromagnetic field. And so we can see then that, so this tells us, and what we learned last time is that electromagnetic fields carry energy and momentum. And in fact, we saw that to conserve momentum, you have to consider the momentum of the electromagnetic field. That was one of the things we learned last time. Now, this idea of electromagnetic fields carrying momentum and energy and momentum is best seen when we talk about waves. Oops, let me get this. So this is best seen in the case of electromagnetic waves. For electromagnetic waves, you can really see how the waves carry energy and momentum. Okay, so now what we're going to talk about is, what is an electromagnetic wave? And that's a big question that we want to answer today. And how do they behave? And they're really important, and you guys already know that they're important because that's when you turn on your radio, that's where the sound is coming from. It's carried by electromagnetic waves. And so what is an electromagnetic wave? How do they arise? These are big questions. And how do they behave? Now, today we're going to really focus on this first one. What is an electromagnetic wave? And later, we're going to really focus on how do they behave. But how do they arise? We're going to be a little soft on that, because that's more of a topic for the next semester, Physics 110B, the details of how they arise, radiation, how antennas radiate. It will be a topic of Physics 110B, but we'll talk a little bit about this question too. But for this class, it's really the what and how is more what we're going to focus on here. Let's just to start the topic off though, let's just say a few things about how do electromagnetic waves arise. Let's just sort of approach it from a qualitative point. How do they arise? And the bottom line is when you accelerate charge. Accelerate charge. Charge. When we accelerate charge, we get electromagnetic waves. And a way to see that, you can see that pictorially, very easy. Let's just consider a charge. So this is sort of a hand-wavy graphic explanation. So let's consider some charge, Q. I'll say plus Q, it's positive. And then you see that I have this electromagnetic field that's pointing out radially. You guys know this. That's the electromagnetic field. And then let's consider that this would be, say, at time t equals 0. But now let's consider a little bit later time. Let's suppose that it's accelerating. Let's suppose q is accelerating. And then what's going to happen is that you see that at some later time, you're going to have this situation. You're going to have the original electromagnetic field here. That's where it used to be, say. But then at some later time, you're going to be here. The charge will be here. It will have moved. And so it's going to be here. So let's draw the electromagnetic field. It's going to be like that. So you can see that at some later time, I'll call this t equals delta t, and then I'll call this t equals 0. And you can see that the electromagnetic field has shifted. It's changed. It's totally different, right? If the charge has moved, the electromagnetic field has to move along with it. But think about that, what that means for a second, though, because the electromagnetic field extends to infinity. And so does that mean that this gigantic object which stretches out to infinity is going to move instantaneously with the charge? That's pretty ridiculous, because then that would violate the speed of light, because then because this electromagnetic field extends 1,000,000 light years away, and it cannot move instantaneously. And so what that means is that what really happens at an intermediate time, oh god, that was pretty bad. Let's erase that. At an intermediate time, I'll call it, say, t equals delta t over 2, intermediate time. Then this is the situation. You have something like this. You got the original electric field, say like that. But then at the intermediate time, what happens is you can see that the field hasn't quite shifted yet. There's still some. It's oh shit! Is that doing that stupid thing again? You see that there's going to be some. The electric field is going to have this sort of bendy thing going on. It's going to be bending. It wants to do this new thing, but it's sort of being pulled away from its old magnetic field, electric field. And so you can see how there's going to be a kink where this is the kink. I'll write it here, kink. So you can see how the electromagnetic field has to sort of peel away from the old you can see how the electric field has to peel away from the old electric field to go from the old to the new configuration. And so this kink, that electromagnetic kink, is the electromagnetic wave. Because that kink, it propagates. The kink propagates. And the propagation of that kink is the electromagnetic wave. Okay, so that's light. That's what light is. It's just the propagation of that little kink in the electromagnetic field. So that's that's sort of the hand waving explanation. But now let's do the equations. And I knew you wanted the equations. I know you're thinking to yourself, show me the equations. I want to see the equations. Enough of the little pictures. Okay, so let's talk about the equations. So how do you derive? Let's derive the existence of electromagnetic waves. And it's super easy. That's the beautiful thing. It's easy. It's so much easier than so many of the other derivations that we've done in this class, and that's something that I really like. And it was first done in the 1860s. First done, this derivation I'm about to show you was first done by Maxwell, the famous Maxwell of Maxwell's equations, in the 1860s. So he was messing around with his equations, Maxwell's equations, and he realized, hey, this means that there should be waves, which is kind of a pretty deep insight. Although of course his derivation was done differently, because he was using a much clumsier math technique. We've got our mathematical methods are much more elegant than what he used, because there's been progress since the 1860s in math, luckily. And so let's do the derivation that Maxwell did, but we'll do it a little different than he did. Okay, so so the first thing we do, let's consider Maxwell's equations in vacuum, and we'll add matter later. Let's consider Maxwell's equations in vacuum, and let's see what they imply for vacuum. There's nothing there, so vacuum means no charge, no current. And so we'll add charge and current later. But right now, let's just consider vacuum. And so in vacuum, we have Maxwell's equations are very simple. They are the divergence and curl of the electric and magnetic fields. That's what they are. So the divergence of the electric field, if there's no charge density, is 0. I'll call that let's number them. I'll call that number 1. The divergence of the magnetic field is always 0 because there's no monopoles. And the third Maxwell equation I'll write is the curl. So we see that the curl of the electric field, well, what causes the electric field to curl? And we know what it is. It's changing magnetic fields make it curl. That's Faraday's law. And then what makes magnetic fields curl? Well, we know that it's current, basically, but displacement current in this case, because we're in vacuum. So it's the changing electric field. Changing electric fields make magnetic fields curl. So okay, and so we're going to basically combine these equations. If we combine these in just the right way, then we get waves. Yay, waves. But before we do that, which is a little bit of math, but not much, it's pretty easy compared to other stuff we've done. But before we do that, I just want you to see just conceptually how when you look at these equations, then you see that you have to get waves. Without even solving these equations, just looking at it, you can see that we must have waves. And the easiest way to do that, in my opinion, is first to look at equations 3 and 4. Because if we look at equation 3, then we see that what that's telling us is that equation 3 up there is telling us that if I have a changing magnetic field, then that's going to cause a curling electric field. So the electric field is going to curl around it. So do right-hand rule of your dB dt, but then you got to do the negative of it because there's a negative sign there. And when you do right-hand rule and then take the negative of it, then you see that the electric field, the resulting electric field from equation 3 looks like this. It's curling around the change. So if that arrow is dB dt, then this is the resulting electric field. But equation 4 tells us that if we have a changing electric field, dE dt, if our changing electric field looks like that, then that creates curl in the B field. And now we can use the right-hand rule, and there's no negative sign, so the right-hand rule is easier. It just points in this direction. And that's going to be the resulting magnetic field. And so we can kind of, and so when you put these together without even solving these equations, just looking at it, at it geometrically, you can see that if I somehow am able to create an electric field and a changing electric field, I'll call that dE dt. But I'll just let me just use this dot, that dot, E dot, that's the changing time derivative is the dot. So if I am able to create somehow through an acceleration of charge a changing electric field, then you can see how that's going to create, then it's going to create some resulting magnetic field. But if the changing electric field is changing, then that's going to create some changing a magnetic field, but that magnetic field will be changing, and since that changes, then you can see that from here, dB dt, that's then going to, when you do the right-hand rule, then you can see how that's going to have to create a changing electric field. And then I'll call that E dot. But if I have an E dot, then you can see from here that that's going to create a changing magnetic field, B dot. But if I have a changing magnetic field, that's going to create a changing electric field, E dot. Okay, I think that's enough. You know how I like to just keep going on this kind of stuff. But you can see how you're getting this crisscross pattern. Crisscross pattern of cascading E and B. And that is what an electromagnetic wave is. That's an electromagnetic wave. It's this crisscrossing, because I have a changing E, which creates a changing B, which creates a changing E, which creates a changing B, which creates a changing E. And from these equations 3 and 4, you see that it's all happening at right angles to each other, because the changing of one field creates the other field at right angles. So it's this weird crisscross pattern. That means, crisscross means at right angles. Okay, so that's sort of just, okay, so that's just kind of conceptual, but now let's do the equations. So now let's actually do the math. So what we're going to do is we're going to take that equation. So what we're going to do, the math is pretty easy. We're going to take equation 3 up there, and we're going to do, I gotta move it up. We're going to do del cross, let's take equation 3, and let's just hit it with del cross. Let's take curl of equation 3. And when we do that, this is what we get. We get del cross. Now there's equation 3 up there. See it? You see it up there. There's equation 3. I'll circle it. So if we take del cross of both sides, then what we're going to get is del cross of the left-hand side is del cross E. And then that's going to be equal to del cross, the right-hand side is negative dB dt. So let's do that. So this is just del cross equation 3, basically del cross of Faraday's law. And then what we get then is, using the vector identity of this guy, we see the vector identity is del cross E is del of del dot E. This is just a vector identity. It's on the inside cover of your book. Minus del squared E. And that is going to be equal to negative dB dt. That's going to be equal to, on the right-hand side, pull the derivative out, negative d dt of del cross B. Okay, pretty easy. But now, since we're in vacuum, there's no charge density. So del dot E, which is normally charge density, but now it's equal to 0 because there's no charge density. And del cross B is equal to, we see that del cross B is equal to, that's equal to mu naught epsilon naught dE dt. Because it's dE dt that creates curl in B. And so if I have curl in B, then that's the same as dE dt. So then this gives us negative del squared E is equal to, and then I got the time derivative here, and I got a time derivative here, and so that's going to be equal to negative mu naught epsilon naught d squared dt squared of E. All right, and so that means then that I have, I'll rewrite it like this: d squared dt squared of E is equal to 1 over mu naught epsilon naught del squared E. And that is it. So simple. That is the wave equation. Oh my God. It's the wave equation. And it's really huge. It's a really big deal. And we can see that what it means is that the second derivative in time is proportional to the I'll write it here. The second derivative in time of an object, of a quantity, electric field, is proportional to the second derivative in space. So it's basically saying that, well, I guess there's no simple other way to write it other than just the equation. But the second derivative in time is proportional to the second derivative in space. And the constant of proportionality, this annoying thing. The constant of proportionality is the velocity squared. That is the wave equation. I'll write it again like this. So you can say, d squared f dt squared is equal to, well, let's just write it like this. First, I'll write it like this. If the second derivative of some function is proportional to the second derivative in space, then that's basically the wave equation. But the constant of proportionality, d squared f dt squared, equals whatever that constant proportionality is. Constant is the velocity squared. The constant of proportionality is the velocity squared. So you guys have all seen it before somewhere, I know, in other classes. But now you see it in E&M. And you might be wondering, well, wait a second. Oh, let's put the little vector sign there. You might be saying, well, wait a second. That's just for the electric field. What about the B field? So what we did was we took the curl of this equation to get the wave equation. But we can just as easily do it the other way. Del cross this equation also gives it to us. So either way works. And so let's just do it the other way really quick since it's so important, because what we can do is we can do del cross the curl of that equation 4, which is Faraday's law. And if we take the curl of equation 4, then what we have is del cross B is equal to del cross mu naught epsilon naught dE dt, and then this side, for using just the vector identity, or the vector calculus identity, it's equal to del dot B minus del squared B, and that equals mu naught epsilon naught dE dt of, and I can bring the curl inside. It'll be del cross E. Gotta get all these vector signs. And then we see that this is 0 because there's no monopoles. And then we see that this del cross E We know what that is. That's just equal to dB negative dB dt from Faraday's law. And so plugging these things in, we get negative del squared B is equal to mu naught epsilon naught of negative d squared dt squared of B. In other words, d squared dt squared of B is equal to 1 over mu naught epsilon naught del squared B. The second derivative in time of a quantity of B field is equal to the second derivative, is proportional to the second derivative with respect to space. And the constant of proportionality is the velocity squared. It's the same one. And we know what that velocity is. The velocity is, so that means that the velocity of the wave is 1 over square root of mu naught epsilon naught. And when you take the square root of that product, then you get the very famous number that we all know and love, 3 times 10 to the 8 meters per second, the speed of light. Ta-da! So simple. So I really like that derivation. It's just so beautiful and simple. And so that means that E and B satisfy the wave equation. And what that means is that E and B can move like a wave. Yeah, they can move, and when they move pretty fast at 3 times 10 to the 8 meters per second. Okay, folks. So right now, what I'm going to do is, some people have requested that I sort of point out the breakpoints within the lecture, because the lectures are feeling quite long to a lot of people, and so this is a natural breakpoint. This is a time in which you can go turn this recording off and go take a break, do whatever you want. This is a good breakpoint right here. But what I'm going to do, I'm not going to take a break. My work is never done. I'm not going to take a break. I'm just going to continue with the lecture, but you can take a break at this point, go eat lunch, do whatever you want, and then you can come back and finish the lecture later. So this is a nice break point right here. Okay, but now, okay, well, I'm assuming you went and took a break, so welcome back from your nice relaxing break. I did not take a break, but I'm gonna just keep going. I'm glad you took a break though. So let's keep going. And so what we're gonna do now, we see that E and B satisfy the wave equation, and so E and B can move. And so what I want to do now is, since waves are so important, let's talk about the properties of waves. Properties of waves in general. And so this is really didn't write that well. In general. And this is really a math digression, but it's important because we need to understand the math of waves. Math digression on waves. Because I need you guys to remember what waves are and how they behave. And some of you have taken a course very recently and you remember waves, but some of you haven't for a while, so maybe you're a little rusty on waves. So let's talk about properties of waves in general, and that's what we're going to do right now. That's for the rest of this lecture. But then what's going to happen in the next lecture is we're going to talk about we're going to apply these properties to electromagnetic waves. But right now, we're just going to talk about waves in general. And so let's remind ourselves, what the heck is a wave? And so a wave is a solution to this equation. And you know what equation that is? A solution to the wave equation. And here's the wave equation. Let's just do it in 1D. Let's just do everything in 1D because that's easier. And the wave equation in 1D says that I take the second derivative in time of some quantity. I'll call it u. I don't even have to tell you what u is, just some quantity. And that is proportional to the second derivative with respect to space. D squared dx squared of u in space. And so if the quantity u satisfies this equation, then u is a wave. And so, but what is u? So the solution, then a wave, is this. It's the solution, and the solution to that equation is this. U of xt is equal to this. There's two possible solutions. I have f of x minus vt, and I have another one, I'll call it h, and that's x plus vt. These are the solutions to this equation, the wave equation. And so this is my wave. Now, you might not have seen it written like this. Some of you might, this might look familiar to some, but this might look unfamiliar to some others. So maybe you haven't seen waves treated quite like this, but that's okay. It's always good to see something new if you've never seen this. And so this f is the right moving wave, moving wave, and this guy, h, is my left moving wave. And I need both of them to be solutions because waves need to be able to go in both directions, in all directions. And so let's first, before talking about f and h, let's show that this is a solution. So show it's, let's show that u of xt does solve the wave equation. And I think it's useful to do a little math right now because it's so important. I mean, come on, waves are so important. You wouldn't be able to listen to the radio without waves. You wouldn't have light, so you wouldn't be able to see, and you wouldn't be able to get a tan and go to the beach on a sunny day. So it's very important. This is the math behind it. So let's see that these guys are a wave. So let's write out the wave equation, and let's write it like this. Here's the wave equation: d squared dt squared minus v squared of d squared dx squared acting on u of xt is equal to, you guessed it, 0. So because I'm just taking I was just taking this guy and just pulling it over to the other side. And so that means I can rewrite the wave equation like this. I can say that this is d dt minus v ddx times d dt plus v ddx acting on u of xt equals 0. Okay, so that's my wave equation. And so now let's plug in the solution. U is equal to f of x minus vt or h of x plus vt. And let's do them both separately. And this, let's define this as gamma. Gamma equals x minus vt. And this guy we can call beta. Beta equals x plus vt. And so then let's plug this f in first. And so when we plug f into here, we have d dt minus v d dx. And then we have d dt plus v d dx acting on f of x minus vt equals, now we want it to equal 0, but let's test if it really does. So let's call this, since I can call this gamma, then basically I have this is f of gamma, and I can think of this as h of beta. Then when I take these derivatives, it looks like this. I can have this guy hits him first, so I can write this as d dt minus v ddx. And now when that derivative, when this time derivative hits him, what is it going to do? Well, it's a chain rule. Just a simple chain rule, no big deal. It's going to be df d gamma times d gamma dt. And then now when the spatial derivative hits him, same thing. Let me fix this gamma. And now I'm going to plus v, and now d dx is going to hit him, so it's going to be df d gamma times d gamma dx equals, and this equals what? Well, let's see. I have here d gamma dt. Now, what's d gamma dt? D gamma dt is equal to, because if gamma equals x minus vt, then d gamma dt is, you can just see it, is minus v. And what's d gamma dx? Well, if gamma equals x minus vt, then d gamma dx is 1. And so what we get is, you can see it already, we get d dt minus v ddx times, this one is minus v df d gamma, and this one is plus v df d gamma. And of course, that equals 0, because these things cancel. Yay, it equals 0. And then we notice we didn't even need this left part, but that's the one that if we do it again, that's the one that's going to act on, if we plugged in h, so we just proved that that's the right moving solution. We just showed that the right moving wave is a solution, f of x minus vt. But if we plug in the left moving solution, h of x plus vt, then we see that it's going to be this one that causes it to go to 0, using that same kind of math. Then same math. I'm not going to do it. You can do it on your own. Same math gives 0. So it's a solution. So we see that both the right moving and left moving ones are solutions. Okay, so that's a little bit of math, but what does it mean? What does it all mean? What does it mean? Well, what it means is that the wave, what it means is that the wave can be anything, any goddamn thing, can be any f of x minus vt or h of x plus vt. So basically, where f of gamma and h of gamma, well, beta I use, are any function. So the wave really can be anything. So it's really very general. It's because I know you guys are always thinking of waves as like sine waves, and we will talk about sine waves. That's like the most important ones. But really, it's much more general than that. For example, suppose, let's do some examples. Let's do an example. Suppose I pick a random function. Suppose we pick this function, f of x is equal to e to the negative x squared. That's a Gaussian. And so can that be a wave? Can I have a Gaussian wave? Well, let's see. So if I pick this, this is just a random function, a Gaussian. So here I am, here's my Gaussian, let's plot it. This is f as a function of x, and we can see that it looks like this. Right? That's e to the negative x squared. Okay, it's just a familiar Gaussian. Can that be a wave? Well, yes, of course it can be. So then the wave u of gamma is equal to f of gamma is equal to e to the negative gamma squared. And so my wave, then my right moving wave is u of xt is equal to f. I'm sort of writing it all out just so you can see all the steps, but it doesn't have to be quite so tedious, but is equal to e to the negative x minus vt squared. Now, what the hell does it mean to write e to the x minus vt squared? Well, you can see right away what it does is this thing means what it's going to do is it makes you move to the right. Move to the right. Because as time goes on, then what happens is this number gets bigger as time moves on. And so basically this guy is my t equals 0 solution. But when I look at my wave, I see that a little while later, it looks like this. Because it has shifted. T equals delta t solution. But then if I wait a little bit longer, I see it has shifted more. T equals 2 delta t. And if I wait a little bit longer, it shifts even more. It's the same function, it's just moving to the right. T equals 3 delta t. That is the wave. It's basically, it just means that I take a function, I just make it fly off to the right, and that's my wave. It solves the wave equation. And so a wave equation means that this is a possible solution. So that means that this disturbance that I just wrote, this Gaussian disturbance, can move through my material. And so this is a very general thing. And so the idea is that then you can say, well, what is you? What are we even talking about? Well, the beauty of it is that we can be talking about anything that solves the wave equation. And what are things that solve the wave equation? I could have a string. Strings solve the wave equation. And so then u is the vertical deflection of a string. Vertical deflection of string. I could have waves in the ocean, water waves. We need those to surf. I could have water waves. Water waves. Thank God for water waves. And then u is equal to the vertical motion of the water. Vertical motion of water molecules, right? Of water stuff, molecules, whatever. That's what a water wave is. I could have sound traveling through metal. Sound in, whoops. I could have sound in the air, or in a metal, or in a material. Sound in any medium, and then u is equal to the pressure. It's equal to a compression, a pressure disturbance, pressure increase, local pressure. I'll just call it the local pressure, because then I can have a wave of pressure. And so I think you and I know you've thought of these things before, but I'm just pointing it out. I think I started this conversation it's a little bit backwards in a sense. I'm going through the math, and then but these are then talking about these other applications. But I just want to remind you, you guys have seen these in other classes, and so you're familiar with waves, so you know that any of these quantities, the vertical deflection of a string, the vertical motion of water particles, the local pressure of some material, these quantities all satisfy the wave equation. Satisfy wave equation. And so we can then get the disturbance. So then we can get then we can get a disturbance in U propagating. Disturbance in U propagates. So we can get a propagation of the U of either the vertical deflection or the vertical motion or the local pressure. And so now the point is that now what we've just proved today in class is that U can also be the electric field or the magnetic field. It can be electromagnetic fields. And so then the point is now that E and B can move like a wave. And so I could have my E of x at t equals 0. I could have it look like a Gaussian. It could be, say, E naught e to the negative x squared. That's perfectly fine. And then I can have that disturbance travel. Then I could have, if I want, I could have E of xt, and now I can travel E naught e to the negative x minus vt squared. So now I have this weird Gaussian wave, E of x, where this is E versus x, and it's traveling to the right with some velocity. And you know what the velocity is? You know that the velocity is 1 over square root of mu naught epsilon naught, which is equal to c, our favorite little velocity. Okay, and so that, and of course I could have the wave moving in the opposite direction, right? I could have h of x minus vt. I could have it equal to, using this Gaussian example, e to the negative x plus vt squared. Oops, x plus h. So this is my left moving wave. This is also a solution. This is also possible, left moving wave. I just want to point out that they can move to the right and the left. And so, okay, but what is our one of the most useful wave, a use, so let's consider a very useful wave, a wave which is really one of our very favorite waves, a very useful wave. A particularly useful wave is if I make the choice of, let's choose the function f of gamma is equal to a sine k gamma. So that's just some function. It's just some random function. F of x is equal to one of our favorite functions is the sine function, sine kx. And so I can make a wave out of this function, because this function, we're very familiar with it. It goes like this, and that would be f versus x, and so this is just one choice. So I can choose this particular wave, this particular function, and if I do, then the wave that I get from it is u of xt. Let's make it be a right moving wave. It'll be then f of x minus vt, and then that will be a sine k times x minus vt. And if I do that, then let's just do the math a little bit further. Then I get u of xt, the wave, is equal to a sine k times x minus, and then I have k times v times t. Now, just for fun, let's give this part a new name. K times v, let's call that omega. So let's just define omega is equal to k times v. All right, that's a definition. And so if we make that definition, then we see that this particular wave is looking like this. It looks like this. It's a constant a times sine kx minus vt. Oops, I screwed that up. Kx minus omega t. And so this is one choice of wave, but this is really one of our very favorite waves. This, of course, is our sine wave. Yay, sine waves. And we love this wave. And if we start looking at all these little quantities, then we can start seeing that this particular wave is very nice because it's periodic in space, lambda. We like this wave a lot because it's periodic in space with lambda, but it's also periodic in time. Periodic in time, which is the period t, period. And so and we can also see here, just from the definitions, the amplitude is a. And we can see that this wave is moving to the right with some velocity v. And what we have is we see that there's a if I have the period t is going to be equal to 2 pi over omega. So that's the period, and the period in space, lambda, is going to be 2 pi over k. So it's periodic in space and it's periodic in time. And so that's very convenient. Very convenient, because then I can use this as a nice basis state to construct other functions. Nice basis state. And we can use it to build other solutions. For example, I could build some new g of xt is equal to, say, some sum of k's of a sub k sine kx minus omega t. All right, and so so these are, because they're periodic, because the sine waves are periodic in time and space, we can use them as nice basis states. They're very convenient for constructing other solutions. Okay, and so I know this is all very mathematical, but you've seen all this math before. It's mostly review, but it's important for this class. And so now we're ready for our most favorite wave, our bestest favorite lovable wave, most favorite wave, the one we love the most. We love them all, but there's one that we love the most, is this one. Our most favorite wave of all is this one. Are you ready? It's this one. It's when we choose this function, f of gamma is equal to a e to the I k gamma. Yay! That's our favorite one. We love him. We love him so much. This is our favorite wave. You've seen them before. And so if we plug in, if we have a right moving wave, to make it move to the right, a right mover, then we have gamma is equal to x minus vt. And so then we would have a right moving wave u of xt is equal to f of x minus vt is equal to a e to the I k x minus vt equals a e to the I kx minus omega t, right? Where omega is equal to k times v. Okay, so this is our favorite wave. You've all seen him before. The complex exponent u of xt equals a e to the I kx minus omega t. And you know the formal definition of this function, of course, is, you know what it is. It's a times, let's write it like this, cosine kx minus omega t plus I sine kx minus omega t, which of course looks kind of complicated at first, but it's really quite beautiful. It looks complicated, but as we all know, it makes the math very simple. Looks complicated, but makes the math very simple. That's why we love it. Makes the math simple. And that's why it's our favorite wave. It makes the math simple. It makes the math so simple. We love it. It helps us to understand things. And so how do we visualize it? There's different ways to visualize it. How do we visualize it? It's a complex number, right? Complex number. Oh my God. So complex. It's a complex number, but and so you really can't visualize a complex number. I mean, really, it's an imaginary thing. But on the other hand, there is a way to visualize it that you have all seen before, and we visualize it using the complex plane, and we think of it as a phasor in complex plane. And this is how you can visualize it. This is the best way to visualize it. So you have this. In other words, it's just an arrow that spins around. An arrow that spins around. That's all. It's just a spinning arrow that spins around. That's all you got to do. It's just remember that it's a spinning arrow. And this is the air. And so this, so if I have f of, how should I best write this? If I say, if I have f of x minus vt is equal to a e to the I, let's see, why don't I write it like this? U of xt equals a e to the I kx minus omega t. Then it's an arrow that's spinning around. The arrow has length a, and it's spinning on the complex plane. And so this is the imaginary part of u, and this is the real part of u, and they're spinning. And this is the most important thing. This is the phase, phi, and the phase is kx minus omega t. And so it's spinning because that phase is growing. It grows in time and space. And that kind of makes sense because the wave is moving. And so the wave is moving, and so if I think of it as, you know, zipping along with some velocity v, then where v is equal to, of course, omega over k, then you see that if I move in space from here to here to here, I can see that the phase is changing, right? So here, for example, I could see that. Here, for example, I could say that phase is 0. And then here, when it crosses, I could see here that, oops, no, that would be, I'm sorry for, well, it depends whether it's a sine or the cosine. Let's talk about, this will be, here we'll talk about the imaginary part of u. Then I can say that this point is where phi equals pi over 2. And so you can see that as I move in space, the phase changes, but also if I'm just standing here looking up at it, then what I see with my eye is this thing is moving along. And so I can see that the phase changes in time too. Phi equals a function of time. So the phase is growing in space or time. Another way to think of it, so a way to visualize this, the wave, if I have this wave, u of xt is equal to a e to the I kx minus omega t, what we can do is you can put an arrow at every point in space. Here I have an arrow, and then the next point in space I have this arrow, then I have this arrow, then I have this arrow. So put the arrow at every point in space, but make sure that the phase is changing at every point in space, and then and then they all spin. They all spin in time. So that's a way to visualize a wave, is it's sort of like taking an arrow and putting an arrow at every point in space, at every point. Then, but the phase changes in space. The phase as a function of position is equal to kx. So at every different position, the phase is different, but then they all spin in time. They all spin in time with the angular frequency omega. Oh, that wasn't too good. With omega. Okay, and so I know that you've all seen this before, so this should be review, but still, it's important. That's why I sort of went over this, because we'll be using this, and a very nice thing is that any function, any other wave, f of x minus vt, can be written as a linear superposition of these guys. Any other wave can be written as a linear superposition of these waves, e to the I kx minus omega t dk. So I can add up these waves, and I can build any other wave out of them. So they are excellent basis states for building up other functions. And of course, this is also a Fourier transform. And that's why Fourier transforms are so useful. Well, they're useful for many, many reasons. But the price we pay for all this mathematical beauty and mathematical simplicity, the price we pay is that physically, if I talk about a physical quantity, if we do a calculation, then any physical quantity can only be either the real or imaginary part of it. Physical quantity, for a physical quantity such as E or B or something else, then we have to take the imaginary part of it or the real part of it to get physical meaning. And you might ask, which one? Which one? Well, that can depend on the details. It depends on the boundary conditions. But the bottom line is you the idea is keep the wave u of xt as a complex number during any calculation, and then but basically what we do is we take the imaginary or real part at the very end. And this is a mathematical strategy that you've all seen before, I think, but I'm just sort of reminding it of you again because this is what we'll be doing a lot in this class. Okay, folks, that's a good time to stop. Thanks. Bye-bye.